Hello everybody, thanks for being here. So today we will talk about VirtualBox and Windows. So the exploit we presented at Point 1, so we'll showcase some detail about it in a 30-minute presentation, so it will be quite fast, and let's start the presentation. So first we will introduce the context. We will introduce the context and talk a bit about Point 1 and about ourselves. Then we will talk specifically about VirtualBox, and finally we will finish with the Windows part. So my colleague here is Thomas Bouzerar, and I'm Thomas Imbert. We are both working at Synactive. And Synactive is a French offensive security company doing pen testing, reverse engineering, and so if you're interested, feel free to come talk with us after the talk. So Point 1, I think there is already a presentation about some stuff presented at Point 1, so I'll be quick. But it's an ethical hacking contest. And we decided to participate to the Point 1 Vancouver 2023 edition in March. And we targeted Oracle VirtualBox with the add-on, which was the Windows local privilege escalation. So the goal was to chain VirtualBox guest to host escape with Windows LPE, so from the VirtualBox privileges to the system privileges. And we had 2 months to prepare that and to win a good amount of money. So let's talk about VirtualBox. So VirtualBox is a very popular virtualization software. It's a type 2 hypervisor, which is open source, so it's very good for us for security analysis. And it has multiple components, but to simplify, there is some VirtualBox driver doing some stuff, and some VirtualBox VM process inside in user mode in the host. And we, for the competition, we will be inside the virtual machine, which has its own kernel, its own application, and we'll be starting from the virtual machine and trying to attack the host. So how do we do that? Actually, the virtual machine needs to have access to external devices, such as the keyboard, the mouse, the emulated disk. And all of this is handled inside the host. And so to get the sense of the attack surface, for example, if we take a device access, for example, you hit the disk MMIO, the memory mapped IO, within the virtual machine, it will trap inside the host, and the VirtualBox driver in ring 0 will forward that access to the VirtualBox VM process. And this process run in ring 3, and it handles most of the interrupt, IO, emulated device, and it has even an instruction emulator. And so all of this is an attack surface from the guest to the host, and it's parsing untrusted data from the virtual machine. So it's interesting for us, and this is what we will target in the next slide. So I'll pass the talk to Thomas to continue on VirtualBox.
Thank you. So VirtualBox has a quite large code base, and back when we started looking into it, we had no prior knowledge of the target. So one may ask, where do we start? And so the first thing we did is that we checked the latest available version, which was the 7.06. It was released in January this year. And the previous latest major update was version 7.00. And it introduced a few new virtual devices, such as IOMMUs and virtual TPM. It also open sourced additional modules, such as EHCI and XHCI, and added support for secure boot for EFI systems. According to Point 1 rules, we have now the guest operating system which runs Windows 11. So TPM might be a device of interest here, as we will see just now. Because TPM stands for Trusted Platform Module. It's a secure crypto processor, which is mandatory since Windows 11. And it's quite easy to interact with, so that makes it an interesting first device to look at from an attacker perspective. So the first thing we did is that we grabbed for TPM in the code base, and we had a few matches, which we will go through. First, we have libtpms, which is an open source library used also by QEMU. It's capable of emulating TPMs. Its main purpose is to be embedded in hypervisors. And so now it's time to dig in the code really of VirtualBox. So we have the dev.tpm.cpp file, which manages the virtual TPM from the VirtualBox side. Then we have a few implementations of an actual virtual TPM. The first one is drv.tpm.mu.cpp, which implements a virtual TPM using swtpm, which is yet another library. Then we have the drv.tpm host, which simply bridges the host TPM to the virtual TPM. And finally, we have the drv.tpm mu.tpms, which uses the libtpms we've seen just earlier. And if we read through the code, we can quickly just focus on two of those files, because in the default settings of VirtualBox, only the drv.tpm mu.tpms implementation is used. So the one using is libtpms. So now, if we look at the way the TPM is handled by VirtualBox, dev.tpm.cpp just creates a new virtual TPM and does a few things each time we create a new VM. First, it creates a new MMIO region for the VM and registers read and write handlers for this MMIO region. And then most of the TPM emulator logic goes through libtpms, which is in ring 3. So any invoked method from ring 0 will simply jump to the ring 3 implementation of the libtpms. So now we can just look at the MMIO handlers in themselves. So we can look at the read handler. It's quite simple. It's simply a wrapper on another function, which it gives a stack allocated buffer. And then we have this mem copy, which seems quite dangerous. So it copies data from a buffer into the stack allocated integer, and it copies CB bytes into it, but there is no check on CB, so that makes it just a simple stack buffer overflow. So it was really trivial to find this stack buffer overflow, because the first file we opened, we just found this vulnerability. And we have a control stack buffer overflow to a stack allocated buffer with controlled buffer, because the AB CMD resp buffer is used both for input commands and response data from the virtual TPM. And finally, the CB is the read size requested by the VM exit. So now we have to trigger this bug. So we have to control the CB value to make it more than 8 bytes. So how would we do that? Well, we had a few ideas. First, we have instructions which trigger atomic loads of more than 8 bytes. For example, AVX instructions or x87 instructions. frestore, for example, just pops a FPU state from memory, and it's quite large, so you can trigger a nice load in this MMIO region and trigger the overflow. And then we have another idea, which is using DMA, but at this point we have opened only one file of VirtualBox, so we don't even understand the architecture of the hypervisor. So how can we exploit this vulnerability? So far we don't have any information leak. So our first approach was that Windows DLL-based addresses are aligned on a pretty large memory range. So we could do maybe a partial RIP overwrites and jump to a nice gadget that would create us an info leak by copying host pointers into our response buffer. And the gadget then has to continue the execution so that we can trigger the bug a second time to get code execution. So we need control over the size of the overflow to do the partial RIP overwrite. And thankfully, it's quite easy to do DMA in VirtualBox. We have a few nice functions for doing that. And they go through the MMIO handlers in case of MMIO addresses, so this is perfect. We can trigger our stack buffer overflows this way. And there are many wrappers around those two functions, and even wrappers around the wrappers. So basically, we just grab for physread, and we try to find what can use for this. And we found a nice match inside a VMM dev device. It's a virtual device which is used for host and guest communication. Most of its features are disabled, but the device itself is enabled for a few things. And we can do we can use the host guest communication manager, which is a simple request sent from the guest to the host. It's a simple RPC protocol, and the format was well documented by other researchers who might be in this room. And we have a few arguments that can be controlled in the HGCM request because the call parameters may be either integer or buffers, and in case of buffers, they are read from the guest memory through DMA. So now we have a way to basically trigger our stack buffer overflow with controlled amount of bytes. We just use HGCM request. So we remap first the MMIO region to a virtual address. Then we just use a HGCM request with a buffer parameter, and we give it the remapped virtual address and arbitrary size. And finally, we get a proof of concept, which gives us a full partial of RRP, so either full or partial of it. So back to our initial approach, we were trying to create our own info leak, and we need to override part of the response buffer with those pointers. So we searched for such a gadget, but unfortunately, there was no suitable gadget in VirtualBox. So we had to find a second vulnerability to get an info leak. So we decided to look back at the PGM physRead function, and we wondered how it works under the hood. So when we want to read data from the guest memory from a virtual device, we call PGM physRead, and the PGM physRead function will do the memory read page by page. So it will read page by page and return OK once it's done. And what really happens when it tries to read one page, it first checks if it's a normal page. If it is, then it will simply memcopies the data into the destination buffer. But if it's not, it will check if there is an MMIO read handler associated to this page. And if so, it will just trigger the MMIO read handler, as we've seen earlier. And if it's not the case, it will just memset the destination buffer with FF bytes. Then all of them will continue the execution to the next page read. But there is an edge case in case of MMIO read handler, because what happens if the read handler actually fails in the middle of a read? Well, it will just memset the destination buffer with FF bytes and return an error. But that means that it won't go through the next page read. And so you might end up with an initialized memory past this part of the buffer. So we have a nice information leak. If any call to PGM physRead does not validate the return value, we can leak any kind of data. So if the PGM physRead tries to read into a stack buffer, we have a stack info leak, and if it reads into a heap buffer, we have a heap info leak. So that's pretty strong primitive, and we can abuse it to get an info leak. But to do so, we have now to find a good leak candidate. So we need a call to PGM physRead which does not validate the return value. We want it to read in a stack buffer because we want to exploit the stack buffer overflow, so that's pretty good to get return values from the stack and eventually stack cookies. And then we have the device. We need the device to write back the data to the guest memory so that we can read the leaked data. And we found a nice match in XHCI because it does a lot of physical read and write accesses, and it copies data from arbitrary physical addresses to other arbitrary physical addresses. So that seems like a good candidate, and we found this nice method which basically reads data from the guest into a stack buffer. Then it copies the data into another buffer and writes this buffer back into the guest memory. So what this means is that if we manage to make the physRead fail in the middle of the read, we will end up with a stack info leak and of almost 1 kilobytes of data. And thanks to this information leak, we get return values and stack canary from VirtualBox in the guest memory. And actually, for performance reasons, there is no stack canary in VirtualBox. So we don't even need that. So we have 1 kilobyte of data just to leak one return address. So now we can defeat ASLR, build a rope chain, and execute a shellcode. And the shellcode is quite straightforward. We first resolve external symbols that we need for next step. And we use, once again, pgm-physread to read the second stage PE file from guest memory. Then we write the PE file in the host system, and we call winexec to execute the second stage. And then we have a 100% reliable VM escape. Now I will let Thomas talk about the LPE part.
Thank you. So now we are running code in the host, and we have still to escalate to get an administrator shell. So we are running code in the host with the same privilege as VirtualBox had. So it's the VirtualBox VM process, which runs as unprivileged user, but with medium integrity level. That means that it's not running inside the sandbox. So we have a very large Windows attack surface to elevate. But for point-to-one, we have to use the kernel mode vulnerability. It's in the rules, so we have to find something in the kernel. We cannot use RPC services or IPC or COM or sorry. So where do we find target? So we decided not to spend a lot of time on point-to-one. So usually what people do is that they enumerate all the attack surface and they pick something depending on the interest. But for time-limited project like this, I decided to get lucky and just pick a few drivers that looks to do some parsing of user mode data. And after, so I went through the file system in Windows 32, System 32 drivers and pick a bunch of drivers and found some bugs. But for most of them, I could not load the driver because to load the driver, you need to be administrator. So I was hoping to find a driver that is not loaded, but that could be loaded using services, RPC trigger, or anything else. And I got lucky. I found a good candidate, which is MSKS SRV, which stands for Microsoft Kernel Streaming Service. It's part of Microsoft Streaming component, which is used in the multimedia component on Windows. And it implements content streaming between two processes. Content could be the camera, audio, or video feed that is streamed between two processes. And under the hood, we use shared memory. And what's good about this driver is it's loaded on demand. So you don't, actually when you look at the kernel, it's not loaded. But when you open the device path, the plug and play system will load it for you. And it doesn't require administrator access to load it. So it's perfect because we have some bug in it and we can load it. So I will talk about how does it work internally for you to better understand the driver and then the bug. So let's imagine we have one process A that wants to share data with the process B. So it will open the driver that will load the driver and then initialize some global context using IOCTR and same initialize the stream with an ID 1. And then that process B can do the same, open the driver and register to the stream ID 1. Well, only one process can register to a stream, so it only works between two processes. And then they can start sharing data using another IOCTL. They want to transmit, the process A wants to transmit two buffers. And the kernel will receive the address and the size of the two buffer. And the thing is, here it won't copy the data from the process A buffer. It will save the virtual address, the size, and the physical address inside the memory descriptor list. And it will not memcopy the data. And then the process B can consume and receive those two buffers. And similarly, here it won't copy the data. It will map. So the kernel will map the buffer inside process B memory. So it will be different virtual address that points to the same physical address. And so at the end, we have process A and process B that share buffer. If you write to the yellow buffer in process A, it will be reflected in process B. So this is basically share memory. And so, yeah, that's good, but where is the bug? The bug is actually the MSKS driver does not validate the virtual address of the buffer. So you could use a buffer in user mode, or you could specify a buffer in kernel mode, and that's okay. So you can basically ask the kernel to map itself to user mode with read and write privilege, read and write permission, and it will work. And so this is a vulnerability that is quite powerful because you get arbitrary kernel read and write by design. And the technical detail, it's that the MSKS SRV driver is using probe and log pages, and it's specifying the kernel mode flag, which says to the kernel that this access is trusted and they don't have to validate anything. But actually the address comes from user mode, so it should use user mode flag that will probe and validate the address, validate that the address belongs to user mode, but they forgot that, so they used the wrong flag, and the fix is actually just changing that flag. And so now you get arbitrary kernel read and write. But if you specify a virtual address that is not valid, it will crash because it has to be mapped. So we need some KSLR bypass or something like this. Fortunately for us, we are not in the sandbox, and Windows by design also give you the address of the kernel mode address of object. So if you have an handle to an object, it has a kernel mode structure inside the kernel, and using anti-query system information with the handle information, you can get that kernel mode address. That will be fixed in the next Windows version, I think, but it was working for .1. And usually for privilege escalation, what we want to target is the process token, which is the things that describe the process security context, so the user running it, the group, and the privileges. And so we can just use this API to get the kernel mode address, and then use the vulnerability from the driver to map it to user mode with read and write. So we can directly read the token and write to it, corrupt it. So yeah, it makes privilege escalation easier, and we can just override the token privilege, get all privilege on the system, and there are many ways to escalate at this point. We used SODebug privilege to hijack a process that was running a system and spawn a shell from it. And so, ta-da, we got a system shell. And the bug is very powerful. The missing probe bug are very powerful, so it's stable. So that's good for the exploit chain, because if we have one bug that was not really reliable, for .1 you only have 3 tries, so that's good. Both our exploits are reliable; it shouldn't fail, and the exploit is very fast. And one fun fact, or not so fun fact, is that we didn't spend a lot of time looking at this driver. We found the bug, and after a few hours, we got some working exploit. And after the fix was released by Microsoft, and some articles were describing the vulnerability, some people found that there was a bug very close to this bug, and it was exploited in the wild because I didn't notice it. I was looking at the driver very quickly. The driver is very small, so there's not a lot of feature, but I missed the bug, and people and Threat Actor found it and exploited it in the wild. So not to myself. Next time I do .1, I'll try to find if there is another bug in the same surface to avoid Threat Actor targeting people. And that's it. So we got the chain working, and I will let you finish.
Okay. Thank you. So to conclude, we had quite simple bugs. We had a few low-hanging fruits, but we had to find them in the right places. So while the bugs themselves were quite simple, we still had to dig in either the drivers or in the case of VirtualBox, we had to dig in the low-level APIs to find them. But we found nice bugs, and we had no real trouble in exploiting them because there was no stack canary in VirtualBox. So we could just smash the stack like it's 2010. And we had relatively weak mitigation in Windows because the KSLR is weak. And we had a 100% reliable chain, but our first attempt failed because we forgot to disable Windows Defender. And so our second stage was flagged by Windows Defender because of the suspicious API used. So yeah, don't forget to disable it if you try .1. In a 3-bug chain, we had 2 unique bugs and 1 bug collision for the stack buffer overflow in VirtualBox. But we still won point-to-one thanks to our great team of Tinactive with other exploits of operating system, such as it was exploit in macOS you have seen this morning, and other exploit in Tesla and so on. So in the end, it was quite a fun journey, and you should try playing point-to-one if you haven't already, because it's fun. Thank you. And if you have any questions, we'll be happy to answer them.